First of all, of course, I would like to thank the organizers for giving me the opportunity to present our latest results here today. And at University of Innsbruck, we are using superfluid helium nanodroplets to study the structure and reactivity of metal clusters in order to model the catalytic processes. And in heterogeneous catalysis, the reactants A and B typically face high reaction barrier. And in order to overcome this barrier, high energy input is required. And this is typically in the form of high temperature or high pressure. And this makes the reaction very costly and overall unsustainable. A catalyst can provide an alternative reaction pathway which will lower this reaction barrier. A new era in heterogeneous catalysis started in 1989 by the discovery of Haruta and his co-workers that supported gold nanoparticles can be a good catalyst for oxidation of CO even at the low temperatures. And since then, typically inert gold, which was never discovered to be, which has never been interesting for a catalyst, has attracted a lot of attention, and number of papers per year on the topic of gold catalysis has exploded, showing that sub-nanometer sized nanoparticles hold high potential for the development of highly efficient catalytic materials. And this is not only valid for gold, but also for other metal clusters. And since then, a lot of different catalytic materials has been discovered, and some of them are even used at the industrial scale. But in order to rationally design a new catalytic materials, we need to understand what exactly happens on the surface of the catalyst. And we need to discover the reaction mechanism basically at the molecular level. And our approach is to isolate the active site of the catalyst in gas phase by modeling it with the gas phase clusters. And the active site of the catalyst is mainly these metal nanoparticles. And then we can study this isolated reaction. And it gives us the opportunity to discover the intrinsic catalytic properties of metal clusters, which are unperturbed by the surrounding. We can also have the full control over the charge, structure, and the composition of our active site. And clusters itself are also very interesting because they have size-dependent physical and chemical properties which are non-linear and also very different from that of bulk, meaning that even the addition of one atom can change the catalytic properties of the cluster completely. And because we are using a very small clusters with a size from 1 up to 10 metal atoms, we can use it for the benchmarking of the computational methods. So the goal of this study is to understand the role of the metal particle in the catalytic processes to increase its efficiency. And today I would like to focus on two great carbon sources, CO2 and acetylene. Both are linear molecules in the gas phase, and they can be used as a building blocks for many different chemicals. But in order to form any of them, a catalyst is required. So if we look at quite not simple reaction, but hydrogenation reaction, for example, to produce methanol from CO2, it has been shown that copper-4 can be a good catalyst and can also lower the required pressure for this reaction. And for the hydrogenation of acetylene to ethylene, gold is promising one. So in this talk, I would like to answer the questions: what do the clusters look like and how do they influence the structure of the reactants? But I'm not going to describe you the whole catalytic circle. I'm going to talk about the formation of so-called entrance complexes. So the first part of the talk will be about the copper CO2 complexes, and then I will tell you something about the gold acetylene complexes. But to form these complexes, we required superfluid helium nanodroplets, which are created due to the supersonic expansion of pre-cooled helium gas through 5 micrometer nozzle, and we typically use the temperature of 9 Kelvin and the pressure around 20 bar. And this brings us in the regime which is known as fragmentation of liquid. In this regime, we can produce droplets with an average size about 1 million helium atoms. And those droplets are quite big, and their geometric cross-section is proportional to their pickup cross-section, meaning that we can pick up any gas phase atoms or molecules. The droplets have also quite low internal temperature of only 0.4 Kelvin, which allow us to do a helium tagging not only for positively but also for negatively charged ions. And these droplets are transparent in a wide range from UV to IR light, making it possible to use them as metrics for the spectroscopy studies. But we are not just using the droplets, we are using multiply charged helium nanodroplets. So here you can see such a droplet which contains 1 million helium atoms, and those red dots are charges. Unfortunately, I discovered that this video will not work, so you have to use your imagination. So those charges act as a nucleation center and they attract metal atoms. Metal atoms start to agglomerate around the charges and the energy comes free, which dissipates then in this helium bath, resulting in the evaporation of helium from the droplet, and the droplet shrinks. But simultaneously, the clusters cool down. So we can create several clusters in just one big droplet, and depending on the initial charge of the droplet, we can create either positively or negatively charged ions. And to answer the first question, what do the clusters look like? We use the instrument which is called TOFI in our lab, where we first create ions, create droplets, then we mass to charge, then we ionize the droplets, then we can bend them into the pickup region, where then the droplets are doped with the metals, and metal is sublimated in the ceramic resistively heated oven. So the droplets are flying through this region, the clusters are formed, and then the droplets shrink a little bit, but still not enough. So we are not able to detect it with a time of flight mass spectrometer. So in the next step, what we do is we liberate our ions by colliding them with the room temperature helium in the hexapole chamber. And depending on the pressure in this chamber, we can select how many helium atoms remain attached to our ion. As a next step, we have the possibility to do mass to charge selection in the quadrupole, and then to do, for example, collision-induced dissociation studies, which are not the topic of today's talk. And in the end, we detect ions in a time-of-flight mass spectrometer. And here you can see example of the mass spectra that we obtained for copper clusters, for cations and anions, which are solvated in up to 100 helium atoms. So basically, each bomb is a different cluster size with many heliums attached. So now, what can we do with this? We can use helium as a chemical probe in order to study something about the structure of our clusters. And for this, we are looking at the magic numbered ions. And those are ions which have particularly high intensity. And they're typically formed by the fragmentation of unstable structures into a more stable ones. So these magic numbered ions are the very stable configurations, let's say. So as a next step, what we do, we plot the ion yield versus number of helium atoms for each different cluster size. And here you can see examples for cationic and anionic copper 4 and 5. And you can immediately spot these magic numbers, which are also indicated in red. So now we know which configurations are the most stable. We ask for help our colleague Michael Gatchel from the University of Stockholm, and he has calculated how the clusters look like with this particular number of helium atoms attached. And since helium atoms are very weakly bound to the cluster, if the structure of the cluster is wrong, there is no way to stabilize it computationally, and the helium will just fly away. So what he found is that for copper 4 in both cases we have a rhombic structure, while for copper 5 cations we have a transition to 3D structure, and we find the twisted bow tie, while for anionic copper 5, it remains planar and we find half of a wheel structure. In this way, we have obtained the structures for many different cluster sizes, and now we know how our active site look like. We can make a next step and react it with CO2. And now we are going to answer the question, how do the cluster influence the structure of the reactant? And for this, we are using a next instrument, which we call Klastov, and this one has the possibility to do spectroscopy. And this is quite similar. We produce droplets, then we ionize droplets, we dope the droplets, but then instead of using helium to liberate our ions, what we do is we collide the whole droplet with the surface, and the helium-tagged ions are backscattered from the surface and guided with a series of electrostatic lenses into the time-of-flight mass spectrometer. But before we detect them, we irradiate the ions with a tunable IR laser in order to perform photodissociation spectroscopy of helium-tagged complexes. So how does it work? First of all, we obtain a mass spectrum. For example, here is copper 4 with CO2 and with different number of heliums attached to the ion. Then we irradiate our ion with the IR light, and if the light frequency is resonant with one of the vibrational frequencies in this complex, the light will be absorbed and it will lead to the dissociation of helium from the complexes. What you can see is then decrease in the ion yield of helium-tagged complexes and increase in ion yield of the bare ion. So this is basically formation of a photoproduct. And what we do further is we trace this increase as a function of the laser frequency. So basically when the light is not absorbed, we see nothing, and as soon as we see some fragmentation, we see a peak. And here you can see IR spectra that we have obtained for cationic copper clusters reacted with CO2. CO2 has 3 fundamental vibrations, and asymmetric stretch is the strongest one, and I have shown it here with a dashed line. So what you can immediately see that the frequency that we observe is quite different from the free CO2, meaning that cluster has some influence on the structure of the CO2. So now I plot the position of this asymmetric stretch as the function of the cluster size, here in blue. And Tibor Holz and Matezalai from the University of Budapest have also calculated the CO2 asymmetric stretch frequency in black. And you can see that they're quite nicely following each other. And what you also can observe is that with the increasing cluster size, the position of this frequency comes closer and closer to that of free CO2. If we look at the binding energies, it becomes immediately clear why is it the case. We can see that copper 1 has the lowest binding energy, so this bond is the strongest. But with increasing cluster size, this bond gets weaker and weaker, trying to approach 0. Therefore, the frequency that we measure comes closer and closer to that of free CO2. What they also found is that for all cluster sizes that we have investigated, CO2 is bound in and on configuration, but not by charge transfer as was expected originally, but rather by the polarization. So there is no charge transfer between CO2 and cluster, a very small one, but it's rather attracted by the forces within CO2 and cluster. So energy decomposition analysis has shown us that when we have only one copper atom, so copper B, which is attracted then to CO2, then all the charge is on this copper B, making this oxygen A very electronegative. But when the cluster starts to grow, since we have only one charge all the time, this charge starts to be distributed among all the copper atoms in the cluster, so the charge on this copper B decreases. So there is no need for oxygen A to be so negative anymore, and its partial charge starts to starts to increase until it basically reaches the equilibrium where both oxygens are 0.5 and basically doesn't fill the cluster anymore. And now I would like to tell you what happens when the gold clusters react with acetylene. So previously in our group, the cluster structure of cationic gold was already determined using neutral helium droplets. And now I reacted with acetylene, and here you can see the IR spectra for cluster sizes from 1 up to 4 atoms. And acetylene has 5 fundamental vibrations. We are going to look at the CH stretch, shown here with the dashed line, and again we see that the position of the band that we measure is quite off. You can see it here in the black, and Johannes Reichager and Milan Onchak have calculated also this position in black, in blue experiment, and black is the calculations. And also here, similarly to what we have seen before for copper clusters, with increasing cluster size, the position of the CH stretch comes closer and closer to that of free acetylene. And the binding energy shows us that the gold one forms the strongest bond, and with increasing cluster size, the bond gets weaker and weaker. But this bond is actually still quite strong, even for gold 4. So in all cases, this cluster form a T-shaped complex by formation of coordination bond, which means that we break a triple bond of acetylene, and both carbons each forms one bond to a gold atom from the cluster, and thereby we weaken the CC bond and also CH bonds. So the symmetry is now broken, and molecule is not linear anymore, and it's ready to react with other molecules. But as soon as we change charge, we see something different. So now we have investigated what happens if we use anionic gold instead of cationic gold. Some calculations on the surface have predicted that by changing the doping on the support, the charge on the gold atom can be changed, so it can be positively, gold can be positively or negatively charged, but in both cases the acetylene is reacting exactly in the same way. However, what we observe is quite different. First of all, we see 3 peaks instead of 1, and if we compare the position of this band to that of cationic gold, we see that it's shifted by almost 300 wave numbers, which is quite a lot. So we had no time yet to perform any calculations, but we did have time to look into literature, and we found that anionic halides also show the CH stretch around the same value as what we measure, which is already closer than that of cations. And this study suggests that acetylene is bound in end-on configuration. So we suspect that in this case, gold binds acetylene by the charge quadrupole forces. And also, like I've shown you before, an example of copper, we can see that with increasing cluster size, the charge on the gold, which is connected to acetylene, decreases, and therefore this band shifts closer and closer to that of free acetylene. So the interaction gets weaker and weaker with the increasing cluster size. So I have shown you that we are able to determine the structure of the metal clusters using helium as a chemical probe. We have also investigated how copper clusters react with CO2, and we found that for all cluster sizes, CO2 is bound by physiosorption in end-on configuration, which is dominated by polarization. The acetylene is bound to cationic gold clusters in a T-shape by formation of strong coordination bond, and the acetylene gets activated. But as soon as we change charge and study interaction of anionic gold clusters, we see formation of other type of complex where the acetylene is bound in end-on configuration, probably by charge quadrupole interaction. And in all cases, we see the strong cluster size and charge dependency, with monoatomic ion being the most active one. And I would like to thank NanoBio group from the University of Innsbruck under the lead of Professor Paul Schreier. I would also like to thank Fabio, Anna Maria, Martin, and Johannes for helping me with experiments, Johannes and Milan for performing calculations on gold acetylene, Tibor and Mate for doing calculations on copper CO2, and of course Michael for doing calculations on the structure of copper clusters. And you for your attention.
Thank you, Olga. Very important work on actually determining the structural properties of these clusters. Do we have any questions here from the audience?
So what about the copper anions? Because to activate CO2, you need to bring one electron there. So I'm not surprised to see that the CO stays linear. But I would expect if you take a negatively charged cluster, it will be very happy to donate an electron to CO2.
Yes, I haven't studied copper anions yet with this method. We are working on it. But I've studied carbon-doped copper anions using free electron laser Felix in Nijmegen. And there we see a very interesting size-selective behavior, which is indeed not linear. And we see activation, so bending of CO2 or dissociation of CO2 depending on the cluster size.
Yes, please.
Thank you very much. Nice, very nice, Olga. The first part on the copper clusters and the CO2, you explained that the helium disappears. At some point, also the CO2 will disappear due to the infrared laser. And how do you disentangle that, or is it only at high cluster sizes?
Not unfortunately, but we don't see dissociation of CO2. Our laser is super weak. It's nothing in comparison to the free electron laser.
But how would you distinguish that? Because you see all the masses at the same time. How would you know that if you measure on copper 10, that it's actually not coming from copper 11 and the CO2 loses? How would you know that?
We are looking at the production of copper CO2, right? So basically, if we will lose CO2, we should see something also on the copper channel or on the bare copper. And there we don't see anything. We have seen something like this for anionic gold clusters with acetylene. There we see really dissociation of acetylene from the complex. So we see something in the channel of bare metal ion, but for copper we don't see this.
Okay.
Do we have? Yes, there is a question in the middle.
Yeah, thank you for a very interesting talk. I was wondering, like, now you make these copper CO clusters, so the other ones outside the helium droplet?
No, they're first formed in the droplet, and then we break the droplet to only get few helium or few hundred heliums attached.
But then, so you first have the copper cluster, and then it collides with the CO2 outside the helium droplet? Or is the CO2 also inside the
CO2 is also coming into the helium droplet,
okay.
and then we break the droplet.
Okay, thank you. Okay.
Are there any other questions? So, okay, yes.
I'll go ahead and ask. So, correct me if I'm wrong, but you showed that the bigger the copper deposit on the CO2, the more it returns to the original CO2 structure. So I'm wondering about another vibrational transition, right? So one of these vibrational transitions is forbidden for symmetry reasons. And so as soon as you would add copper to it, it should become somewhat allowed. And then does that also go ahead and disappear as you go? Would that go ahead and disappear? It's a different one than you measured, right?
Yeah. Again, at Felix, I measured with a free electron laser. We're actually not using helium, but we break CO2 from the complex because the laser is much stronger. There we studied up to 25, and we always see all of them basically.
All of them.
So maybe we need to go bigger, but this I don't know.
Okay, very interesting.
So I have a question. Actually, whenever you want to reduce CO2 or let's say acetylene, for example, then you also at some point need another reagent. So in the beginning, of course, with CO2, you need to transfer an electron to it. But is there a chance that you could actually look at the binding of two different species to a cluster like this? Can you actually measure it, or it becomes too complex?
Again, at Helix we did. Here the problem is, at this point, we were not sensitive enough, because more you bind to the cluster, smaller your peak gets. But now we are rearranging the machine and introducing a quadrupole to do mass selection, and then it should be possible, but it can take another year until the machine is rebuilt, let's say.
Mm-hmm. And when it comes to the binding strength or the binding affinity, that's quite clear that the smaller the cluster, then the stronger it is. But can you, for example, determine a limit, or just think how possibly to determine it that, okay, let's say at this size of the cluster we actually lose the catalytic effect, or it becomes very, very weak?
I would guess that we can do it either with calculations, because calculations seem to, at least for small clusters, they work quite well.
Mm-hmm.
And otherwise just measure bigger clusters, I would say. But again, we are a little limited with this method because we are using oven, and oven can only get to 1,200 degrees, and we need to heat up more, we need to produce more vapor to make bigger clusters.
Okay, thank you. Is there anyone else who would like to ask something to Olga? If not, let's thank Olga again.